Hello everyone, my name is Mridul Gupta. I am a PhD student in Computer Science and Engineering at Santa Clara University, located in California, the United States of America. I'm affiliated with the SCU Internet of Things Research Lab under the esteemed guidance of Dr. Behnam Desfoli. I'm here to present our work titled AirXDP, a flexible and efficient user space data plane for Wi-Fi access points. This paper was recently accepted at the 11th IEEE Conference on Network Softwarization. Let's get started. Our motivation is the rapid growth of Wi-Fi usage by IoT devices, computers, mobile phones, which has necessitated the need for creating Wi-Fi access points that are efficient, flexible, and offer ease of monitoring. Currently, access points rely heavily on the Linux kernel for packet switching. This dependency on the Linux kernel has a few major drawbacks. First, the Linux kernel is a generic architecture. This results in incoming packets traversing multiple components in order to be compatible with various protocols, resulting in increased processor utilization. Second, modifying the Linux kernel's data plane requires extensive knowledge of the kernel development to prevent disruptions to its normal operations. Current monitoring tools often lack flexibility, provide only coarse metrics, and struggle to scale for modern networks, which demand fine grained real time monitoring. Hence, we need to look at methods that would rather utilize the user space for packet processing. Current user space methods, such as the data plane deployment kit and vector packet processing, require high amount of processor resources and are also requiring NIC support. Therefore, our goal in this paper is to introduce a user space based architecture that does not require explicit NIC support, is easy to modify and monitor, and at the same time is efficient and high performing. Let's talk about the architecture of AirXDP. This diagram displays the high-level overview of the system architecture. AirXDP is based on AFXDP, which was introduced from Linux kernel version 4.8 onwards. Hence, it does not require explicit driver support. The first major component of AirXDP is the XDP redirect program. This is a kernel program that is attached to the NIC on its ingress end. The responsibility of the XDP redirect program is to forward ingress packets from the kernel to the user space. Certain rules can be created within the XDP redirect program so as to only forward those packets that are of importance to the user. There are two different attach modes. One, the generic XDP mode, the second, native XDP mode. We will talk about the differences between the two in the next slide. The next major component is the packet processing engine, or the PPE. This is a user space program consisting of two parts. First, the user memory, or the UMEM. It is a memory space created by the user to allocate memory to the four queues of AFXDP: the receive queue and the fill queue on the ingress end, and the transmit queue and the completion queue on the egress end. It is in these queues that the packets reside. The next component of the PPE is the packet switching function, or the PSF. This is a queuing algorithm that we created in order to efficiently move the packets across the four queues. It should be noted that when packets are transmitted using AFXDP, they inherently bypass the queue disk that is present on Ethernet interfaces. As a result, this creates a mismatch between the Wi-Fi and Ethernet paths. Since Wi-Fi interfaces do not have any queue disk and instead have the active queue management scheduler used by queue disk or Ethernet interfaces built into the MAC 8.11 module. In order to have parity between the two paths, that is, the data flowing from Ethernet to Wi-Fi and Wi-Fi to Ethernet path, we have modified the MAC 8.11 module to bypass this AQM schedule. This is also shown or highlighted in the system architecture diagram here. Now we look at the differences between the native XDP mode and the generic XDP mode. The diagram here provides a high-level overview between the differences in the two modes. First, the XDP redirect program, when using the generic XDP mode, suffers from two bottlenecks. Firstly, the XDP redirect program attaches to the NIC after the creation of the socket buffer. As a result, some level of packet processing has already been carried out in the Linux kernel before it is received by the XDP redirect program. Second, the generic XDP mode carries out two copy operations as we can see here. First, one from the driver to the kernel buffer through DMA. The second one is from the kernel buffer to the UMEM that is done by the XDP redirect program. The native XDP mode tries to overcome these performance bottlenecks in the following ways. Firstly, it attaches to the NIC at the earliest point of packet reception, that is, before any socket buffer allocation takes place. Hence, minimal amount of packet processing is done by the kernel in this mode. Second, only one copy operation takes place in the native XDP mode, where packet is directly DMA'd from the NIC to the UMEM. However, it should be noted that the native XDP mode is not supported by all NICs. Hence, a NIC that does not support the native XDP mode reverts back or falls back to the generic XDP mode. Now we talk about the second important component that we created, which is the queuing algorithm or the packet switching function. It consists of four stages. The first stage, which is also the most time-consuming stage, is the sleep stage. This is a user configurable sleep duration that we introduced just before the polling of the receive queue. Without the sleep duration, the number of polling operations on the receive queue would increase substantially, and not all polling operations on the receive queue result in successful retrieval of packets. As a result, this sleep duration allows polling every fixed interval of time, thereby increasing the chances of successful polls and reducing processing overhead. The sleep stage is followed by the peak and buffer stage. Here, packets that were added to the RX queue by the XDP redirect program are retrieved by the user using a polling operation, and the retrieved packets are stored in a user-created secondary buffer. Before the packets are added from the receive queue to the transmit queue, a few checks are taken to determine which kind of packets can be added. The first parameter is if we receive greater than or equal to 32 packets by a single poll operation on the receive queue. However, not all throughput scenarios will be able to give such high packets through one single polling operation. Under low throughput scenarios, it could also be that multiple polling operations also do not receive this batch size. Hence, we introduce a timeout upon the expiry of which all of those packets that were retrieved from the RX queue are added to the TX queue. Next, before the packets are added to the TX queue, the packets are modified. For example, changing the MAC address when performing packet forwarding. Also, these packets go through an active queue management scheduler to drop packets that have a high sojourn time. In order to create an AQM scheduler, we utilize the Cuddle AQM scheduler, which is also the default that is used in the Linux kernel. The sojourn time with respect to AirXDP is the time from when the packet arrived in the XDP redirect program to the time just before it was added to the transmit queue. This helps in reducing the buffer bloat that would be experienced across the four queues in case of ingress and egress rate mismatches. The packets that are added to the transmit queue are then submitted to the kernel for final transmission. The final transmission out of the kernel is done through a send to system call, which is now moving to the send to and recycle stage. It is under this system call that packets are added from the transmit queue to the completion queue for all those packets that were successfully transmitted out of the system. Also, a batch of at most 32 packets can be transmitted out by a single system call of send to operation. Hence, our batch size has been created at 32. The packets that are added to the completion queue are finally recycled back to the fill queue in this stage. This explains the entire life cycle of the packet from the time it entered the receive queue to the time it was returned back to the fill queue. Now we talk about our experimental setup that we used for result analysis. Firstly, we used the access point, which is our device under test. We used two different kinds of access points. The first one that was based on the Raspberry Pi Compute Module 4. This supports the Broadcom Ethernet NIC, which only has the generic XDP mode. As a result, it motivated us to have another access point, which is based on the Xeon X64 server, which has the Mellanox Connect X5 Ethernet NIC that does support the native XDP mode. However, the Wi-Fi NICs on both these access points is the Intel AX210 Wi-Fi 6E card, which only supports the generic XDP mode. We used channel number 185, which works on the 6 GHz bandwidth in an interference-free environment for our data collection. Also, we use the following data configurations for result collection. For example, the XConf1 simulates a single core configuration where both the PSF threads and the interrupt coalescence, which is responsible for kernel level processing of packets, is on core 0. Similarly, XConf3 is simulating a multi-core environment where all four components responsible for packet switching are on four cores. It should be noted that all four cores were isolated and hence the system was not interfering during performance. Also, each core has its own dedicated L1D cache. We collected the following key measurements: the throughput, the CPU utilization, the processing time of each of the stages of PSF, the utilization of all of the rings within the PSF. Now, we look at some of our performance metrics. Firstly, the throughput. We observe that both AirXDP and the Linux kernel achieve the same throughput level. However, when we look at the processor cycles, we see that AirXDP consumes higher processor cycles. It should be noted that these results are for the Raspberry Pi Compute Module 4. As a result, the processor cycles increase for two reasons. First, in the multi-core environment, we have four dedicated cores, whereas in a Linux configuration in a multi-core, we at max utilize two cores. As a result, the AirXDP has lower cache efficiency when packets move across the four cores. Additionally, the Raspberry Pi only supports the generic XDP mode, hence increase in processor cycles. To understand if we could achieve a better processor cycles using the native XDP mode, we ran the same experiments on the Xeon X64 server. We observed first that the native XDP mode consumes 30% lower processor cycles compared to the generic XDP mode. Comparing this to the Linux kernel also showed us that the native XDP mode consumes lower processor cycles compared to the Linux kernel. It should be noted that if both NICs supported the native XDP mode, we probably would have assumed or seen lower processor cycles than what's shown here. Now, to understand why XConf1 and XConf2, which try and simulate the single core configuration, have a lower throughput, we ran some micro-analysis of the PSF rings. The first micro-analysis that we did was trying and understand what is the processing time of each of the PSF stages. One such stage, which is the send to and recycle stage, is shown here. We can clearly see that XConf1 and XConf2 have much higher processing time than XConf3. Why does this happen? The reason being increased context switches. Because in a single core configuration, threads and the interrupt coalescence are always competing for processor resources. Whereas in XConf3, there are dedicated cores for each thread and for each core interrupt coalescence. Hence, there's no competition among the different components. Due to this, the utilization of the queues also increase, as shown here, for example, for the fill queue. We see that there are instances for XConf1 and XConf2 where the queue is completely utilized. As a result, the HTTP redirect program, when it receives new ingress packets, it cannot forward them to the already filled queue, resulting in drop in packets and hence reduction in throughput. This is also the reason why we see an increase in round trip time for packets in XConf1 and XConf2. To conclude, we see that the number of Wi-Fi devices are increasing at an alarming rate. This entails us the need for creating access points that are flexible, efficient, and easy to monitor. To this end, we introduced AirXDP, which is an architecture-independent and easily deployable in the user space data plane of Wi-Fi access points. We introduced a sleep duration in order to reducing the polling overhead on the ingress path. Also, we created a queuing algorithm called the packet switching function or PSF, which was designed for efficient transfer of packets across the 4 queues. We also showed that the native XTP mode, although running on only one interface, still manages to achieve the same throughput as Linux, whereas the processing overhead is lower compared to Linux. The future scope of our work is to try and create packet switching or evaluating packet switching delay under low throughput conditions, where we understand how the timeout variable is affecting the packet switching delay time. Next, if the throughput is low, depending upon the throughput requirements, is a single core configuration enough to achieve our requirements, or do we always need to be using a multi-core? Hence, creating a dynamic core configuration. Also, understanding how we can dynamically change the sleep duration depending upon the requirements of the system. Thank you.